Please join me in welcoming to the Distinctive Voices podium, Dr. Randii Wessen.
You like that story? Good evening. Thank you. What I'd like to do tonight is basically drag you through the solar system. Now, I guess you just can't start and just do that. So the way I was going to break up this talk is first give you an explanation of what the Jet Propulsion Laboratory is, because there are a number of different NASA centers and how it fits in. And then I was going to give you a little bit of an introduction of what JPL is and where it is. And then I was going to break up the talk into Earth exploration, Mars exploration, solar system, and then out into the universe. Now, one of the challenges I have is I can only go about 25, 30 years out into the future, because if I go any further than that, it really becomes to be really science fiction, and it gets too weird. So we're only going to go about 25 years out, but what I hope to do is not give you facts and figures and you try to memorize each mission that's going on, but what I really want you to do is get a feeling that there really is a rational approach to space exploration, and that we are really in the golden age of space exploration as we just go to distant worlds. So with that, in terms of NASA, there are actually 10 different NASA centers, and each one, they're not supposed to overlap. So they all have their own special responsibility. So the Kennedy Space Center in Florida, that's my New York accent, Florida, is the Eastern Launch Range. That's where we launch spacecraft off of the Earth. The Johnson Space Center in Texas, that's where we do life sciences, that's where the astronauts train. Ames up in the Bay Area, that's where we do entry bodies and supersonic research and supercomputers. But JPL does deep space robotic exploration. So with that, the way JPL started is back in the 1930s, Caltech was doing research in a number of areas. There was a small group of individuals that were like building these little baby rockets in downtown Pasadena and lighting them off right there on the campus. Well, those things explode, you know. You'd like them neatly, but they're not necessarily going to be neat. So the administration said, look, guys, you're going to kill somebody. Go up into the arroyo, and if you're going to get someone killed, just do it up there. So they went up there, and they started doing rocket tests through the 30s, using all sorts of toxic stuff like red fuming nitric acid that just goes... Well, the place was getting so big that by the 1940s, they had to name it something. They should have called it the Rocket Propulsion Laboratory, but they viewed that was too much like Buck Rogers. So they decided to call it the Jet Propulsion Laboratory, a division of Caltech. And we started doing gigs for the military. We'd put rocket bottles under the wings of planes so that they can take off on shorter runways and other kind of stuff. But something happened in 1958. NASA was formed. The problem here was that NASA wanted JPL. Caltech didn't want to give it up. So the other 9 NASA centers are all civil service. They're all government employees. JPL is different. NASA pays Caltech to run JPL. So all the wetware, we're considered Caltech employees. The whole facility is government owned. And in 1958, with the creation of NASA, we were called a National Research Laboratory with the objective of deep space robotic exploration. So we're not supposed to fumble around the Earth or the Moon. We're 2 million kilometers, or about 8 Earth-Moon distances out. That's where we start, and we just do solar system exploration. Now, there is a little war going on. What do you call exoplanets around other stars? Does that go to Goddard that does astrophysics? Or is it planetary exploration just around another star system? We haven't worked that one out yet. Now, this is just a great picture. This is our roots. This is where we started. This is Bill Pickering, the director of the laboratory. That's Werner von Braun, who built the launch vehicles for us. That guy is Jimmy. They're holding an engineering model of Explorer 1 that made the first scientific discovery in space. Where Jimmy fits in is we called up Jimmy and said, hey, we're building Explorer 1 and we have a little bit of room. If you could put any scientific instrument in there, what would you put in there? And Jimmy goes, I'd put a Geiger counter in there. So we launched Jimmy's Geiger counter, and as Explorer 1 went higher and higher, it measured belts of radiation. That's Jimmy Van Allen. of the Van Allen radiation belts. So you've got Pickering, Van Allen, von Braun. That's where we started. This is us today. We're about the size of Disneyland. We have about 5,000 employees there. This whole facility is like a city. We have an operating budget of, depending on good years or bad years, somewhere around almost $1.5 billion. And we can have a long discussion of whether that's a good idea or a bad idea. But in addition to building spacecraft here, we also have to listen to them. So we also manage this, which is called the Deep Space Network. This is a series of antennas that are outside of Goldstone, California, Madrid, Spain, and Canberra, Australia. Basically, it's separated by 120 degrees of longitude. So as the planet turns, there's always one spacecraft that can listen to your spacecraft. These things are huge instruments. This thing is 70 meters or about 256 feet across. So picture all that metal. And to give you an idea how sensitive these things are, when my Voyager spacecraft, because that was my first spacecraft, my first love, when Voyager was out at Neptune, about 3 billion miles out, Voyager talks with a transmitter that transmits at about 23 watts of power. That's the power it takes to run the light bulb in your refrigerator. So you take your refrigerator, put it 3 billion miles out at Neptune, open the door. The signal strength that these antennas have to hear after traveling 3 billion miles was roughly 1/billionth of 1/billionth of 1 watt. And remember, it's going to change the function of elevation angle. And now, by the way, Voyagers are now 3 times further out. So we manage the antenna complexes around the world, too. Now, every journey has to start somewhere. Let's start with leaving the Earth. This is a Delta II rocket, and what we did in this, we put a camera right here that's looking straight down. So these things are actually the tops of these solid rocket boosters, and what you're watching is the actual movie of what it takes to leave the Earth. This is not animated, this is not faked, this is not sped up. This is the actual runtime of what it takes to leave the Earth, and we're waiting for that corner to go black. There you can see the shadow of the exhaust on Florida. You'll see the coastline in a minute. But this illustrates one of the problems we have, which is getting into space. If you think about it, a Saturn V was $1 million per pound to orbit. I'm 190 pounds, so that's $190 million to get me up there. If you go on a shuttle, that was $100,000 per pound. These kind of vehicles are like $10,000 per pound, but that's still more expensive than gold. So we're also going to wait for these things to come off. So the trick is you want to figure out a cheap way to get into space, because it's not far. It's only 150 miles up. San Francisco's further away. And you have to do it reliably, because you don't get a second shot at these things. If something goes bad, it goes bad. So now we're going to lose the solid rocket boosters. Come on, drop them off. These are air lit, and they drop them off, and then they just burn up. And any minute, that corner is going to go black, and basically you'd be up in space. So this is where every mission starts. Come on, you can do it. Come on. Come on. Oh, come on. There we go. All right. We're up. That's how long it takes. Not long at all. But it's the toughest part of the journey and the riskiest. So every time, once you're in space, things are really pretty straightforward. But that's the thing that we have to work on. So the first thing I'm going to study is Earth exploration. I'm going to break it up into 3 pieces. When you think of the Earth, you have land masses, you have oceans, and then you have the atmosphere encompassing the whole sphere. What we've been doing probably since the 1980s, pretty much more in the 1990s, is we're having these constellation of spacecraft that go over the whole surface so that you're building up a record of how Earth lives as a system. And if you can study the oceans and the atmospheres and the land masses and put them all together, you can make a model of how the whole system works. So let's look at land masses. This is kind of fun. We use radar light, and we image Los Angeles in this particular image, where you are down here somewhere, I guess. And then if you look at it again with the same kind of light, but after an earthquake, you can actually measure how much the ground moves. So anything of the same color is a displacement of the same size. So you're seeing these fracture patterns of how the land is moving. If you can have models that predict how the land will move, and then you compare it with the actual results, you can refine your models of actually how Earth is moving to try to get an idea of predicting earthquakes. This is fun. We take another thing with radar. We just bounce a signal off the ground, and we listen to the reflection, and we can measure an altitude of the ocean. Now, if you think of the old days how you would do this stunt, You'd start from LA, and then maybe a week later you take a measurement here, and then a week later you take a measurement there, and then maybe a week later you take a measurement there, and then maybe you hang out in Hawaii for a while, then you come out again. Well, with these orbiting spacecraft, you're measuring the whole thing every 5 days, and if you do this for years at a time, notice the days going by, you can actually measure what's going on. So in this particular image, well, movie, red is 10 centimeters, or about 4 inches. That's a 4-inch bulge in the ocean. Purple, that's a 4-inch trough in the ocean. So you're now looking at bulges and troughs moving around the ocean. Well, what makes a bulge? Well, it's hot water. It expands. Cold water is dense. It compresses. So you can see everything going on, and this way you can actually see, oh, 97, you actually watch El Nino happen here, where you just get this massive bulge that just change all the weather patterns, so we get Seattle's rain and other people will dry up. So that's the oceans. Do the same thing with atmospheres. Here again, you'll see the days going by, and though I'm not going to go into all of these things, we're measuring different gases to just get an idea of how the Earth breathes. Because if you really want to ask questions, you know, is there global warming? Is there an ozone hole? You really need to get the data first. And this is what we're doing. We're trying to get the long-term record of really what's going on with the planet. Now, I'm not going to tell you, yes, there is, or no, there isn't. I'm just showing you one piece of the data that scientists look at. If you look at the amount of carbon dioxide in Earth's atmosphere, this is today, this is 50,000 years ago, this is 400,000 years ago. You can see that when people tell you that the CO2 in the atmosphere is cyclical, yes, it is. There used to be a high-level water line here in terms of, this is 280 parts per million. But if you, parts per billion, if you look what's going on since the 1950s, you can decide for yourself whether there is or isn't and what the cause is. But again, we need the data. So what we're doing is we're building new spacecrafts. Some spacecraft have really cool acronyms. This one's kind of weak. This is called SMAP, for Soil Moisture Active Passive. Hopefully they'll get a better name. But what we're doing here is we're going to do global measurement of sources, where CO2 comes from and sinks, where it goes, to try to figure out how the Earth is breathing with CO2. This one we're trying to say about going up in the 2015 time range. Now, one that we just launched, which is really a lot of fun. This is really kind of cool. I'm going to do a demo here. Say I take, I'm a spacecraft, and my car keys. That's a mountain range, okay? If I take two spacecraft and I separate them by 100 miles, as we're orbiting the Earth, the first one actually sees more mass due to those mountain range, those keys. It speeds up as it sees the mountains, and it leaves this one in the dust. And then after this one passes the keys, this one slows up, and now this one speeds up. So by watching how the spacecraft change distances, and we're talking about distances down to a fraction of a micron, one of my hairs, and I don't have many, is 100 microns, okay? So by measuring this change in distance, we can measure how much mass is located underneath the spacecraft. So it's like giving the planet an MRI. We can see where all the mass is located inside. Well, remember I told you we do deep space robotic exploration? Sometimes when we come up with a new technology, we want to practice somewhere before we drag it somewhere, because it'd really be depressing to drag it all the way to Jupiter and then find out it doesn't work. So we tried this thing called GRACE, Gravity Recovery and Climate Explorer. We did the two spacecraft. And it was so successful that we are measuring hot and cold water circulation patterns. We're measuring glaciers melt. So GRAIL, which we just launched in September, is now heading for the moon. It's going to ruin our holiday, so it's going to get there December 31st and January 1st, the two spacecraft. We're going to do an MRI around the moon. We want to see if it has a core. Is it circulating? Try to understand how the moon evolved, which tells us about the other terrestrial planets. And you can tell where we're going with this. Let's drag it to Mars and look for artesian wells and caves. Let's drag it to Europa, the moon around Jupiter, and see how thick the ice fields are. We're just starting this new technology out there. Well, the Constellation program to send people back to the moon has been canceled. One of the challenges they have, and we'll probably find another application for it, is when their LEM-like structure lands on the moon, or was planned to land on the moon, one of the things they wanted to carry were habitat modules, things that the astronauts would live in. Think of them like RVs. Well, one of the problems that people didn't realize was, wow, if you bring a habitat module in a lander, how do you get it off? There weren't any cranes or anything. So we said we'd work on it with a mobility device. This one's got a really cool acronym. This is called ATHLETE, All-Terrain, Hex-Limbed Extraterrestrial Explorer. And it's half scale. This thing has 6 legs where they have an ankle, a knee, and a thigh. And they can either drive or step over things. This is only half scale. This is only 14 feet tall. So you figure 5 wheels down to 1 up, you go almost 30 feet up. And this thing would actually pull the habitat module off. So you could either launch with this thing and land on the moon with this thing underneath, and it just puts its legs down and walks off. Or one of the things we did, which I thought was really pretty cool, is you'd have ATHLETE drive up to the lander. We then designed it to split into 2 3-wheeled objects, which we call triathlete. And it would go to either side of it, stand up, grab it, and then pull it off and come down. Because remember, if you take a habitat module and you bury it in the regolith on the moon, that's not exploration. That's colonization. You make an RV out of it, and now you drive around the world, and maybe you have other nations that want to participate in lunar exploration, drop caches of supplies at different parts around the planet. You then just drive to them. That's exploration. Now we're going to leave the Earth system and go out to Mars. Mars has always been a schizophrenic kind of place in terms of, people thought it was alive, then they thought it was dead, then they thought it was alive, then they thought it was dead. This is why. Mars is about half the size of Earth. It's got some interesting features. It's got a canyon here, Valles Marineris, which would stretch across the United States. So a little dot on this would be the size of the Grand Canyon. It's got 3 small shield volcanoes. There's one. This brown dot's another one. Those you just barely see. Those 3 shield volcanoes are only the size of Mount Everest. The really big one, you can't see it in this picture, it's 3 times the size of Mount Everest with the footprint the size of Texas. Can you picture that thing going off? Like, wow. Now, when we talk about life, there's 3 things we think you need for water, for life as we know it. Liquid water, it's got to be the wet stuff. Ice and gas don't count. Organic compounds, things with carbon and hydrogen, and an energy source. Well, if you look at Mars, and these are 3 different views of Mars, you can see at one point they really look like there were channels cut by something. Maybe water. From the surface of Mars, you can just make out these little white features. Those are water vapor clouds on Mars. And we know Mars has polar caps of frozen water and dry ice. The question was it ever wet? Now, remember I showed you early on with Earth exploration, you saw the bulges in the ocean moving around? We did the same thing with Mars, where we shine a laser down and we look at the reflection and we measure an altitude. Yellow is the reference level, right around here. There's the equator. There's Valles Marineris. There's the small shield volcanoes. There's the really large one. If you look at the southern hemisphere, you see that it's in the yellows and reds. That means this is really high up. And it's heavily cratered, which means it's an old surface. I mean, it got pounded here, which made a big hole in it, but basically it's a high plateau. If you look at the northern hemisphere, you can see it's got some cratering, but very little. And it's blue, which means it's lower down. So think of that as a basin. Well, why is the northern hemisphere so smooth? You could sit there and say, gee, the solar system just hit everything in the southern hemisphere and nothing from the top. Then you've got to explain that. It's a lot easier to say, rather than the solar system just being hit on the South Pole, is that something was covering it or protecting it. The reason why they made this color-coded this way is a lot of people think Mars had a North Polar Sea in the first 500 million years, maybe a billion years of its life. If it did have it, did it actually make life? And we don't know. We know we can't have life on the surface right now as we know it. But how about in its distant past? Well, right now, 2001 Mars Odyssey is it's 11 years old. This is the longest we've had a functioning spacecraft at Mars. This was the first spacecraft to bring what's called a spectrometer, something that looks at the light and gives you an idea of composition of what's on the surface, where we found clues for potential liquid water. So what we did is we built 2 rovers to look for water. Spirit, unfortunately, has now died after 7 years on the surface. It was designed for 90 days. This is a picture from the Mars Reconnaissance Orbiter. This geological feature we called home base. That dot is Spirit. That's its final resting place. Yeah, it was kind of sad when we lost it. This is one of the first pictures of its cameras, of its hazards cameras looking under its solar array out onto the Mars surface, and this is one of its last. But it did a really good job, and we now know that at its site there really was liquid water on the surface, which means you need more of an atmosphere, which means it got warmer, which means you should have had liquid water over the place. The other one, Opportunity, is still driving. One of the problems I want to illustrate is you can see that when we get dust storms, it gets darker and darker and darker on the surface of Mars, and when you're solar powered, that's a bad thing. But what's really cool is when you drive rovers, you have 3 ways of driving rovers. You can do it the really hard way, where you tell each wheel how many degrees you want it to rotate. A more sophisticated way to drive a rover is you give it waypoints. You go, I want you to go to the edge of the stairs, I can't talk. Platform, up the stairs, and then out the door. If you're really sophisticated, the most advanced way is you just give it a goal. We say, rover, leave the auditorium, and you let it figure it out. Well, as you get older, longer and longer to a mission, you can actually make some of these things. And in this case, this is the Victoria crater. We said, okay, Opportunity, drive yourself. We want to get to the Endeavour crater. What's really cool that's illustrated in this picture, you can see the tire tracks. The rover was driving along, and then it stopped when it saw this pile of rocks. It then decided it didn't like it, and then it went around it. We didn't command it to do that. It did that. Now, the game plan was we landed at the Eagle crater. We then drove to Endurance, all the way down to Victoria. That was the picture we just showed you that we were leaving. On this scale, that would be shrunk down to here. That's Victoria. We had to go the 13 miles to the Endeavour crater. The reason why we love craters is if I have a rock on the surface, I can tell you what it's made of, but that's it. I can't tell you where it came from, and I can't tell you how old. If I have craters with sidewalls, and there's rock in there, like bedrock, I know it was made there, and as I get lower and lower down, I know it's older and older rock. So we love craters, even though craters are a really good place to die. They have sand dunes on the bottom where you can get stuck. When you drive too close to a wall, if you're solar powered, you get a shadow as the sun sets, so you have no power and you just freeze. But that's where the most exciting science. So we said, we're not sure we're going to make it, but let's try to go to Endeavour. And we actually made it. On August 9th, we actually pulled up on this massive crater. So we're there now, and we're just going around the rim trying to figure out where we want to come in to actually explore the Endeavour crater. Now, one of the things that we were able to do from the Mars Reconnaissance Orbiter, it's got a radar. Now, we knew the poles have frozen water and frozen dry ice. What surprised us is you'd see a crater in an image, but if you actually explore it with a radar, you find that those things are full of water ice. The dust storms blow ice over the top, so it camouflages the ice so it looks like it's just regular, it's just the surface. But they're all full of ice. What also gets intriguing, this is a picture also from the Mars Reconnaissance Orbiter of the Newton crater. We saw these these dark brown lines coming from the edge of this crater. And what would happen is every spring, these things would get longer and darker, and every fall to the winter, they'd get lighter and disappear. We think this may be indications of water on the surface of Mars today. Now, regular water would just freeze, so we think this is very salty water. But if there's really liquid water on the surface today, that would be a great habitat for something. We just don't know yet. Now, this is how we're going to land on Mars with this new rover we're building. We're going to come in at 12,000 miles an hour. We're going to throw out the heat shield. Right as we hit the atmosphere, we have to orient ourselves to go the right way. So we're going to drop off these little blocks so we're off balance. So now we can turn the vehicle so we can surf into the atmosphere. We're Spirit and Opportunity. We're trying to land in a place the size of LA. We're trying to land in Long Beach. So we're going to steer this thing with the thrusters on the top, trying to slow from 12,000 miles an hour to 0 neatly. We're going to take the heat shield for about 4 or 5 minutes, just using the atmospheric friction just to slow us up. And as we slow up, again, this thing is going to launch this November around Thanksgiving and get there around August and do this. Once we slow up, we have to rebalance, so we have to throw off the rest of the ballast. There, those guys go off. So we straighten back up, and then out of here comes a hypersonic parachute. And that holds us. Now, unfortunately, the atmosphere of Mars is so thin that terminal velocity is about 200 miles. So that won't work. So we drop the heat shield off, and then we have this rover in here wearing a backpack with thrusters. Then we're going to just drop the whole thing, and this thing is then going to be in panic mode as it's going to stare and try to find the ground. So it's got thrusters above it, and it's in a panic mode looking for the ground. Now, as we're going down and getting closer and closer, it's trying to figure out how far away the ground is. We're going to make a movie of this. We've got a camera that's actually on the bottom of the rover looking straight down. It's called Marty. It's right over. Come on, where are you, Marty? There you go, right in there. This thing is going to make movies, so you can actually, I mean, it's really to show where we actually land, because since there are no landmarks, it's tough to figure out where you are, but it makes a great PR piece. It's really kind of cool. Anyway, once we see the ground, we're going to lower the whole rover away from the descent stage. We call this the sky crane concept. We're now going to measure the tension in each one of these cables. The loose one is really for command and power because the rover is doing the driving of the descent stage. We're going to measure when the tension goes to zero. When the tension goes to zero on those three lines, we're going to fire charges to cut the cords. There's going to be no weight. The descent stage is going to pop up, and then it's just going to burn to depletion and crash. But we're down. It's a piece of cake. What's really terrifying about this is to go from the top of the atmosphere to down takes about 6 or 7 minutes. The communication time from Earth to Mars at this point will be about 21 minutes. So when we get data that says, up, Mars Science Laboratory just hit the top of the atmosphere, it's already down. We just want to see whether we have a job the next day, or do we have to go to a Senate subcommittee hearing to explain why we just lost a few $1 billion of spacecraft. But this will be coming to a theater near you. This will be happening next summer, August 2012. We'll have the precise date and time after we launch so we can figure out what's going on. Right now, the launch period goes from November 25th to like December 15th. All right, we're not going to see the whole movie. It's too much. The next thing we need to do is we're trying to figure out where Mars' atmosphere went. Why is it so thin? Well, we know that planets, when they have a core that circulates, they have a magnetic field which deflects the solar wind. But as Mars cooled, it lost its magnetic field, and then protons and electrons from the sun just strip away the atmosphere. We're trying to understand that mechanism so we can try to work back how much atmosphere there really was on Mars. Because again, Mars is a place that we think is most habitable of any place in the solar system. And so this spacecraft, MAVEN, launching in 2013, is going to try to do that one for us. Now, one of the things that's really funny is sometimes, we'll just be minding our own business, doing just kind of science observations, and then all of a sudden we'll get like a weird measurement. Well, we got this measurement from Mars that's really kind of wild. This box is blown up here. This is a measure of methane, CH4 in parts per billion, red being 30, blue being like 0. We found 3 areas that have methane blooms. They're really teeny amounts of methane, but how do you get methane? Methane is usually associated with some sort of geological activity, but we thought Mars was dead. Or it's a metabolic byproduct. Something's going. So we're really curious about what that is. So in a joint mission with the Europeans, a thing called Trace Gas Orbiter with the European Space Agency, scheduled to launch in 2016 to measure trace gases, particularly looking for the methane. And then in 2018, we want to do another joint one with the Europeans, but the problem is it's a rover mission, and we haven't worked out the rover part yet. We don't know if it's half US, half European, which is a recipe for disaster, or do you make one and then you have different pieces. But it's going to use our descent stage, so we're assuming this thing's going to work next 2012. What the National Academy of Sciences has demonstrated, the #1 goal for the next 10 years in space exploration is they want rocks back from Mars. So with the 2018 rover, we thought of this 3-step approach. The first step is you land on Mars and you collect rocks and you put them in a tray. You cache it. You leave it on the surface. Then you send another Mars vehicle with a rover that would pick up the cache of rocks, drive back to the landing pad, and put those rocks on an ascent vehicle that would blast off from the surface of Mars. And then a third spacecraft would come by, watch this capsule coming up, it would rendezvous and dock with it, and then bring it home. So we don't do easy things. I mean, this is kind of how it goes. But what we really would like to do is get samples from Earth, because if you found life, microbial life on Mars, or fossilized life that was on Mars, then you get to ask the next set of questions. Did life start on Earth and then jump to Mars? Or did it start on Mars and jump to Earth? Or did it go both places independently? If it went independently, if you had two genesis in one solar system, then the prospects of life throughout the universe just went through the roof. But we need some data first. One of the things that people don't realize, if you think about how much life is associated in the planet Earth versus on the surface, whether it's in the air, land, or in the oceans, if I put all the life forms from the atmosphere, land, and oceans on a balance beam, but on the other side I put what are called lithotrophs, the microbial organisms that live in the bedrock that go down a couple of miles, if I put the lithotrophs there, that side weighs more. So there's more life energy tied up with lithotrophs than everything else combined. So humans are not the dominant species on this planet. We're just the most egotistical. All right, now we're going to go out into the solar system. This is a picture taken of Cassini of Saturn, and one of the things I love about Saturn that people don't realize, here you have Saturn, here you have the ring system, this is the A ring, this is the Cassini division, this is the B ring, then you go into the C ring, and there's actually a D in here. This ring is huge. If I brought Saturn to the Earth-Moon system, and I had this side touch the Earth, that side would touch the Moon. So when you go out and you see the Moon, just picture that Saturn would just fit in between this thing. But it's only about 100 feet thick. And this is just a sea of ice cubes, just a sea of ice cubes for tens of thousands of miles. But only 100 feet thick. This was the biggest disappointment from Voyager. This is an visual image of Titan, which is the major moon of Saturn. What's really cool about Titan is you guys are sitting in 1 atmosphere of pressure. This is 1.5 atmospheres of pressure. You guys are sucking in 78% nitrogen. That's 98% nitrogen. The two major differences between what you're in and this is, one, there's no oxygen, but you didn't have oxygen on the Earth in order to make life initially. And two, it's really cold. But cold, from a chemistry point of view, just means the reactions happen slower. So we think studying Titan would be like going back in time and seeing what the early Earth was like before it got polluted with life forms. This is a Voyager image. This is a Cassini image. We're starting to see features on it. We even dropped in a probe from the Europeans. This was during descent. We could see channels. On Earth, we say we're by the triple point of water. Water can exist in all 3 states. You can have an ice cube in a liquid water on a humid day. So it's a solid liquid gas. Well, Titan is near the triple point of ethane and methane. So you can actually have ethane-methane rain that goes into ethane-methane rivers, maybe ethane-methane snow that goes into ethane-methane oceans. This is a view from actually on the surface of Titan taken by the probe that actually survived impact. You can see that the rocks are roundish, which means there's weathering going on there. So we know there's energy, we know there's organic compounds, which has led some people to speculate, when we talk about life needing liquid water, can you use liquid ethane surrounded by a fatty membrane exchanging things with the environment? Don't know. We also got a surprise that on Enceladus, we saw these features coming up. It actually has geysers. And we sent the spacecraft and we drove right through these things, and we can see ice particulates, solids, which usually is some mechanical breaking of the surface, but we also saw water vapor, which means there's liquid under here. How do you get a moon this small to have liquid water 1 billion miles away from us? We don't know. But that's another good place to look for life, in the subsurface here. Moving on, we have other spacecraft. Our partners on the East Coast, the Johns Hopkins Applied Physics Laboratory, did Messenger, which did 3 orbits around and finally got into orbit around Mercury, and it's the first orbiter of the planet Mercury. That's going on today. We have a mission also by Applied Physics Laboratory, New Horizons, which will actually get to Pluto in 2015. That's the best image today of it. This is Pluto and its major moon Charon compared to the United States. And that's one reason why Pluto isn't a moon today, because it really is small and it doesn't fit the definition of what a planet is. And if you ask me at the Q&A part, I'll tell you why it's not a planet. But we're waiting to see what this thing looks like. And this is fun. We're actually going to try solar power out at Jupiter distances. Now, this is a cutaway, and these things are radiation belts that just fry spacecraft. We're going to do something fun with Juno. We're going to come in this way, and then it's a polar orbiter. We're going to dive between the radiation belts. So we have a one-year mission, and we're going to try to live for 1 year there, surviving the radiation, doing it all on solar power. So remember, if light goes as 1 over r squared to be geeky, and that's 5 times as far from the sun as us, it means the light levels are 1/25 as bright. So solar power out there is really a challenge. Back at Jupiter, we told you that you got Jupiter, Ganymede. We really like Europa because one of the wild things about Europa, we think it's got a very thin ice crust that may have a liquid water ocean underneath. So if you were looking for life, that's probably one of the hot spots in the solar system to look for. The other mission we want to do, and this is probably in the 2025, maybe 2030 time frame, we know that Titan looks like it has oceans and lakes of liquids. We want to do a 3-part spacecraft that would get into orbit around Titan in the Saturn system. It would orbit it. It would have a lake lander to float in the seas of Titan. And we want to put a balloon with a gondola so it just float at some intermediate altitude just going around the planet. Which would be way cool, but boy, that's not easy to do. Minor bodies. Right now, we have a spacecraft called Dawn that's actually around Vesta, which is the second largest asteroid in the solar system. This gives you an idea. These are to scale of the other asteroids that we've already visited, so you can see that Vesta really is pretty large. We've already made movies of this thing. This is from the survey altitude. Now we're going down from like 1,700 miles down to 400 miles to do the high altitude mapping. This is the size of the next asteroid we're going to do. When we leave Vesta, we're going to go over to Ceres, which is about this size, so it'll be twice the size. And we think these things are intermediates between debris and actual planets. And finally, NASA just approved a mission to go to an asteroid and actually bring back samples. So it's going to go to an asteroid, pick up samples, and then bring them back home so we can actually see material from an asteroid. Now, you're going like, what's so important about asteroids? Here's where I get to scare you. This is the solar system as it looked in 1800. Any red dot you see here is an asteroid that crosses Earth's orbit. Any green dot is one that's outside of it. And in 1800, there weren't any. If we now do 1900, you can see them. Now, first, let me do truth in advertising, okay? Mars and asteroids are not the same size. But on this scale, I have to draw dots this way just to see it. But remember, asteroids are a lot smaller. Now, watch this. This is how many asteroids were known in 1900. This is how many in 1950. This is 1990. This is 1999. This is 2008. We are up to 400,000 asteroids. 5,000 of them are near-Earth objects. They come close to us. 900 are potentially hazardous objects. Now, this is why they scare us. In 1994, a comet, which is just an asteroid with a tail and more ices, came too close to Jupiter and it got pulled into 21 fragments. The big one, the G fragment, was about 1 mile across. When that mile-across object hit Jupiter, we calculated that it released 6 million megatons of TNT. Now, I don't know about you guys, but when I hear million and mega in the same sentence, I don't know what that means. So one of my buddies at work, Don Yeomans, and I tried to come up with an analogy of trying to figure out how you describe 6 million megatons of TNT, which is what you get when you get slammed by 1 mile across ice cube. If you take one Hiroshima-sized atomic bomb, you'd have to drop one every second for 11 years. That's what happens when a 1 mile across object hits you. Now, here's the fun thing. What are you guys doing April 13th, 2029? It's a Friday. There is an asteroid. It's only about 300 feet across, so it's not even a huge guy. For a little while, we actually thought it was going to hit us, but we now know it's going to miss us. It's called Apophos. It's going to come inside a communication satellite distance from Earth, okay? So it's going to be a near miss. Our navigators, who are kind of sadistic, they determine that there's this little region that's, a few meters by kilometers, 1,000 kilometers, that they call the keyhole. If Apophos actually goes through the keyhole, it puts it on a perfect orbit that 7 years later hits the Earth. This is one reason why we have global defense conferences where we're trying to figure out what you would do if an asteroid was coming your way, which is all key to how early in advance you catch it. We don't do Armageddon kind of stuff. That's silly. But we have to figure out what to do with these things, because one of these things hitting you gives you a bad day. The rule of thumb for Earth is that the object that hits you leaves a crater 16 times the diameter. So a 1-mile object makes a 16-mile crater for you. And you can have all-day arguments about which is better to hit land or oceans. It's bad either way you slice it. A lot of people will tell you that the ability to deflect asteroids is the first test for an advanced species. One of the jokes we say is the reason why the dinosaurs aren't alive today is because they didn't have a space program. Okay, final section, universe. When it comes to the universe, there's two big questions we're always trying to figure out since humans could think, and we're actually starting to get our hands on it. One is, where did we come from, and are we alone? Now, at NASA, we are always launching different types of telescopes. This is why. This is the Orion constellation. You can see Orion's belt. There's Betelgeuse. There's Rigel. This is the Orion Nebula. Invisible light. If you took the same photograph in infrared, this is what you'd see. So you can actually see the warm regions and see that the nebula is really a warm region. It's really a stellar nursery. So when you look at it, infrared, visible, ultraviolet, X-rays, in just different wavelengths, it gives you a different piece of the puzzle to really get an understanding of what's going on. Now, this is an old picture, but I love it, and I think they don't do justice explaining it. This is the Eagle Nebula, 7,000 light years away. It would take light 7,000 years to get there and back. This is the Hubble field of view of these three pillars. So I'm going to close up on this. This we call the pillars of creation. This is one pillar. Here's another one. There's a third one. Anybody know what dust bunnies are? Not in your houses, your neighbors' houses. Dust bunnies? Think of these things as massive dust bunnies. Inside there, gas and dust is falling together. It's raining in, and it's getting bigger and hotter, these bulges. And as it gets bigger and bigger and hotter, when it's like 20 million degrees, it starts the fire fusion, poof, becomes round, does hydrostatic equilibrium, and it becomes a sun. That's how you make a sun. So there are suns forming in here. Now for the really cool part. Over here, away from these pillars, but relatively close, is a star that's large, that's already on, and its UV light is boiling away the tops of these pillars. Now, if you're a proto-sun, when I visit that proto-sun, and here's the top of that pillar, the pillar is rarefied gas, so that gets eaten away, but you're thicker than the surrounding stuff, so you stick out, and you act as a shield for everything behind you. I don't know if you can see it from the back, but you see these little pillars sticking up? Those pillars are baby suns being eaten out of their stellar nursery. Now for scale. If you look at one of these fingers and you just go from one side to the other side, that's 10 times the size of the solar system, and this length is 1 light year. It's how far light travels in 1 year, 60 trillion miles. But that's how you make suns. Remember I told you in different wavelengths you can do stuff? Spitzer was cool to look at infrared light. It no longer has any coolant, so it's now doing its warm mission. But some of the stuff you can do with infrared light, here's your garden variety galaxy. It's Messier Object 81. Well, if you look at it infrared, you get to see where all the really hot newborn stars are in it. Looking at this in infrared is like going to Dodger Stadium. Go to Anaheim and give anybody that's under 10 years old a flashlight, and then you turn off the stadium lights and tell the kids to turn their flashlight so you can see where all the youngsters are sitting. I'm going to show you where all the youngsters are sitting in here. Okay, guys. That's where all the kids are. So now you can start looking where you have stellar evolution going into different parts of the galaxy. Are there habitable zones of galaxies? And so on. This is another picture I think they don't do good justice explaining. This is great. When I first saw this picture, I thought it was really boring. This is called the Hubble Deep Field Photo, and this one is the Ultra Deep. The director of the Hubble Space Telescope Institute said, here's what I want to do. I want to take Hubble and put it in the smallest field of view, which is about the size of a grain of rice held at arm's distance. I'm then going to point it to the darkest region of the sky, and I'm going to sit there for 10 days straight. This is the 11-and-a-half-day one. When he got this image where there are about 1,200 objects in here. What I want you to look at is this. And I don't know if you can see it. This guy actually has what's called a diffraction pattern. It looks like a little cross on it. Of the 1,200 objects in there, 5 of them have that diffraction pattern. 1, 2, 3, 4, 5. Now let me tell you what you're looking at. Those 5 objects are 5 of the 200 billion suns in the Milky Way galaxy. Everything else, you're looking past the Milky Way galaxy at the next galaxy of hundreds of billions of suns. Do you have any idea how insignificant we are? I mean, this was a piece of sky no bigger than a grain of rice, and we're not even looking in the infrared. It's amazing. It's just mind-numbing. Well, one of the things we want to do is we want to find planets, and one of the techniques is a thing called a transit, where you look at a bright object and you wait for it to dim as a planet cuts in front of it. Now, that assumes the system you're looking at is edge onto you. If it's perpendicular to you, there's no way you'll see it. The Kepler mission was designed to look at one region of sky and stare at it for 3.5 years straight. Okay? And what it's doing is it's just looking for stars that blink on and off. If it's a Jupiter, the star will dim by like 1%, and if it's an Earth-sized object, it'll dim by 1,000ths of 1%, but it's still measurable. And what we're doing is we're looking at stars that just blink on and off. And here you see just a close-up of a star, and we'll show you what a transit would look like if you were there. You'd have a system, and the stars, the planets that you can't see would actually cause them to blink on and off. Now, those blinks really last for hours, but it's looking for these things called transits. Well, this is the detector of Kepler. Each one of these is a charged couple device. Typically, a camera just has one of these things. This is 42 of them. It took 15 years to find the first 500 extrasolar planets. Kepler found that many with just 3.5 months, 3 months of data. So let me show you what it found. It found 1,235 potential planets in 3 months of data. Of those, 68 of them were Earth-sized, and 5 of them were actually in the habitable zone, which means it could have liquid water. You still taking bets whether we're alone? Well, we want to do other technologies, and we're getting to the end here. One is a coronagraph, something that actually blocks the light from the central star so you can see planets next to it. Another one that we're working on is where you'd have a set of spacecraft all looking at the same object, and then they take their data and they send it to a combiner, which makes one of those. And what that is, it would block the light of the central star, and you would actually see planets around that star system. A direct detection. If you can see the light, you can get spectroscopic data. Spectroscopic data is just looking at the color of light. When you drive home tonight, white light is mercury vapor. Yellow light is sodium vapor. The whitish pink light is high pressure sodium. So just by looking at the light, I can tell you temperature, pressure, composition. If I can actually look at these things, get the spectra out, find out what gases are in the atmosphere, if I find gases that don't belong there, like ozone doesn't belong in our atmosphere. The only reason we have ozone there is because we have life on this planet modifying the atmosphere. You find ozone, it's a biomarker. I couldn't tell you whether it's a microbe or a cow, but I can tell you that that world on that system has life. What are we trying to do? We're trying to find the new Earths. And this, in 2008, was the first direct observation. This is a star. We block it out with an occulting disk. This is kind of noise in the system, but there's some debris here. In this square is this picture. We saw an object move. So we're already doing direct observations of planets around other star systems because we want to find the new Earths, the Terra Novas. Why do we do this? We do this for 3 reasons. One is to just explore a place in the universe because we're curious about it. The next is if you understand other worlds and you bring it back to Earth to understand how Earth works, you get a better understanding how the Earth system works. And then you have all the technology droppings. Ask yourself, was NASA created to form a communications satellite industry, a weather satellite industry, a GPS industry, a remote sensing industry? These are just the spin-offs. You look at your life today versus someone who was alive in 1911, it's a higher standard of living. Ask yourself where that comes from. I'm going to end with 3 pictures here. Well, fourth one, but you don't know that one yet. This is a picture of the Earth as seen from low Earth orbit. This is a picture of the Earth as seen from the moon. There's a little dot in that red circle. That's the Earth as seen from Mars. This is a picture of Saturn from behind. So the sun is directly in the next room behind Saturn. You'll notice there's a little dot there that we had to brighten up. This thing, that's the Earth as seen from Saturn, 1 billion miles out. I'm going to end with a quote now. The Earth is the cradle of the mind, but one cannot live in the cradle forever. Thank you very much.